every time you type a prompt into a frontier AI model, a silent tap starts running. Welcome to the deep dive.
Yeah, glad to be here to really get into this one.
So, for you listening right now, we are about to pull back the curtain on a massive, honestly hidden physical reality of our digital world.
It's a huge shift.
It really is, because
Yeah.
for the longest time, whenever the environmental impact of technology came up, the conversation was completely dominated by one metric, right? The carbon footprint.
Oh, absolutely. The carbon footprint basically defined corporate sustainability for like over a decade.
Right, we tracked emissions, we talked about renewable energy grids, debated carbon taxes, all of that.
And it was really the only lens through which we viewed the cost of computation. But here in 2026, the global conversation has just shifted dramatically.
Yeah, and we should clarify, the carbon discussion hasn't disappeared, but it's really been eclipsed by something much more immediate.
A very visceral crisis, yeah. We are now squarely in the era of the water footprint.
The water footprint.
Right. Because the defining bottleneck of our time is no longer just measured in greenhouse gases, but in the rapid depletion of, well, our most vital liquid resource.
And today's stack of sources paints a frankly astonishing picture of this shift. We are working through a high-impact investigative presentation script called the Silicon Drought.
Which is incredibly detailed.
It is. We're also analyzing some pretty revealing metadata from a YouTube investigative channel called C Capital Clarity, alongside a high-level notebook LM AI briefing guide focused entirely on modern tech infrastructure.
Yeah, that briefing guide really pulls the technical side together.
So our mission today for everyone listening is to understand why the creation of synthetic intelligence is demanding such an astronomical amount of fresh water and what that actually means for the physical world.
And to understand the sheer scale of this thirst, we kind of have to start by completely dismantling how most of us visualize the internet.
Like the whole cloud concept.
Exactly. The prevailing metaphor for years has been the cloud. It implies something, weightless, atmospheric, and entirely detached from the physical earth.
Right, it's just floating up there.
But the Silicon Drought script argues that this metaphor is not just outdated, it's actually actively obscuring a brutal, heavily industrial reality.
Okay, so let's break down that industrial reality. I want to look at the physical evolution of the data center. Because just a few years ago, traditional data centers were essentially just warehouse-sized, aggressively air-conditioned rooms, right?
Yeah, pretty much, they operated on standard HVAC systems.
They used some water for basic ambient humidity control, so static electricity wouldn't build up and fry everything. But the primary resource was electricity, and the output was just warm air.
Right. But those legacy data centers were built for a totally different era of computation. They were designed to house standard CPUs running, linear tasks.
Like hosting websites, routing emails, that kind of stuff.
Exactly. Storing databases. But the hardware driving the neural networks of 2026 operates on a completely different thermal scale.
We are talking about frontier hardware here, specifically the H200 and X100 chips.
Yeah.
So why do these specific chips run so much hotter? Like, what is physically happening inside that silicon that makes them so fundamentally different from the servers we used, say, 5 years ago?
It basically comes down to compute density and parallel processing. An AI model isn't just like looking up a piece of stored information.
Right.
It is calculating complex probabilities across billions of different neural pathways simultaneously. So to do that without unbearable latency, hardware engineers had to pack an unprecedented number of transistors into incredibly dense, tightly clustered configurations.
Just cramming them in there.
Exactly.
Yep.
And when you push massive amounts of electricity through that densely packed silicon to perform simultaneous calculations, the byproduct is just an extreme amount of thermal energy.
And the investigative script notes that the ambient heat from these X100 chips is so intense that if you tried to cool a 2026 hyperscale facility with traditional air conditioning, the servers would literally melt in minutes.
Literally melt. Ambient air simply cannot carry the heat away fast enough to prevent catastrophic hardware failure. Air is actually a relatively poor conductor of heat.
So they can't just blast bigger AC units at them.
No, not at all.
Right.
So to survive the processing power of their own creations, the industry had to abandon air conditioning entirely and pivot to something the sources call evaporative cooling.
Okay, so how does evaporative cooling actually work in this context? Because when I hear that, I picture like a misting fan on a hot restaurant patio, but I imagine the industrial version is slightly more intense.
Yeah, it's a massive thermodynamic operation. So evaporative cooling towers use high-purity fresh water.
Okay.
And it is pumped over immense heat exchangers, basically giant metal radiators
Yeah.
that absorb the extreme heat radiating from the server racks. As the clean water cascades over these superheated metal coils, the water absorbs the thermal energy and undergoes a phase change. It flashes from liquid into vapor and is exhausted out of the facility straight into the sky.
Just plumes of humid vapor pumping out of massive cooling towers.
Exactly.
And the briefing guide highlights a detail about this process that is hard to shake. It is a one-way trip.
Yes.
Once that water absorbs the heat and evaporates into the atmosphere, it is gone from the local watershed forever, which makes the cloud metaphor feel, honestly, incredibly ironic.
Right.
It's less like a floating mist and more like a high-performance athlete constantly sweating out high-purity water just to keep their internal temperature from spiking.
That athlete analogy is actually perfect because it captures the biological urgency of the process. The machines are using the phase change of water as a sacrificial mechanism to dump heat.
Because if they stop sweating,
They die. The hardware fails. And if these colossal warehouse-sized systems are constantly evaporating water every second of every day, we have to look at the granular data to understand exactly how much fluid is actually being lost.
yeah, and the math provided in the sources is where this stops being just an abstract engineering problem and becomes a stark reality.
The numbers are staggering.
The Silicon Drought script estimates the water cost per user interaction. For every 20 to 50 prompts you send to a friend care model, the data center effectively vaporizes a full liter of fresh water.
A whole liter. Consider the processing required for a single prompt. When a user asks an AI to, say, summarize a 100-page PDF or generate a high-resolution image, the model is activating billions of parameters.
Which takes a lot of juice.
Activating those parameters requires intense bursts of electricity, which generates instantaneous heat, which immediately requires water to evaporate to maintain the system's baseline temperature.
So a liter of water for a few dozen prompts might seem small on an individual level,
Sure, if it's just you.
but then you aggregate that across hundreds of millions of daily users globally.
Yeah, and the Notebook LM briefing guide pulls out to the macro level to estimate the consumption for just a single 1 billion parameter model training run.
And what did they find?
Well, the estimates fluctuate based on the specific climate the facility's built in, obviously, but the sources provide a baseline comparison. A single modern hyperscale data center now consumes as much water daily as an entire city of 50,000 people.
That is just crazy to think about.
All of the daily drinking, bathing, cooking, and municipal services of 50,000 human beings, matched by a single building processing synthetic intelligence.
Wow. And the source metadata includes this really striking visual metaphor used by environmental groups to illustrate this. They describe an hourglass.
Oh, right, the hourglass.
Yeah, the top bulb is filled with pristine blue water, and as the water pours through the narrow center, it physically transforms into glowing gold and silver silicon cubes in the bottom bulb.
It visually represents the industrial transmutation of a vital natural resource into a digital commodity.
We are literally converting our most precious liquid into synthetic thoughts.
It's a heaven trade-off.
But the evaporative cooling process isn't a perfectly clean burn, is it?
Right.
I mean, not every single drop of water that goes into the facility turns into steam and floats away.
No, actually, a significant percentage of the water does not evaporate. It cycles through the facility's complex loop of cooling pipes.
Yeah.
And this introduces a secondary environmental issue that the sources refer to as the brine problem.
The brine problem. So if you've ever boiled hard water in a kettle over and over, you see that white, chalky mineral scale buildup on the inside.
Right.
I imagine scale buildup inside the delicate cooling pipes of a billion-dollar data center is a nightmare scenario for these companies.
Oh, it would destroy the cooling efficiency and eventually just burst the pipes. So to prevent mineral scale algae blooms and bacterial growth inside these warm, wet systems, the data centers have to heavily treat the incoming water.
So they're dumping things into it.
Yeah, they add intense concentrations of synthetic biocides, anti-scaling agents, and just really harsh chemicals.
Okay, so the water that cycles through the system but doesn't evaporate becomes heavily contaminated.
Exactly. The liquid that is eventually purged from the cooling loop and returned to the local ecosystem is a highly concentrated, chemical-heavy brine.
Wow.
The narrative presented in the Silicon Drought really shifts here from a story of simple resource depletion to one of active industrial pollution.
Let's trace the logistics of that. A facility is evaporating the clean water out of existence, and the fraction it does return to the environment is a concentrated toxic slurry.
Yeah.
A facility doing this at the scale of a mid-sized city cannot just plug into the water main of a dense urban center like Manhattan or London
Yeah.
without collapsing the local infrastructure. They need space.
And they need dedicated industrial zoning,
Yeah,
which points directly to the geographical data mapped out in the AI briefing guide.
right.
These massive compute hubs are not being built in the rainy Pacific Northwest or regions with naturally abundant renewable watersheds.
Yeah.
They are heavily concentrated in areas like the Arizona desert, parts of Chile, and the Middle East.
Which begs the question, why build the most water-intensive infrastructure in human history in the middle of a desert?
It is a convergence of economic incentives, really. Arid regions often offer vast expanses of cheap land necessary for hyperscale footprints.
Because these buildings are massive.
Huge. But more importantly, they offer abundant, uninterrupted solar energy, which these companies need to power the chips and to meet their remaining carbon-neutral pledges.
Ah, so the land is cheap, the solar power is plentiful, but the water is extraordinarily scarce.
Right, the briefing guide flags these specific expansion zones as areas already facing high or extremely high water stress.
And according to the presentation script, placing these facilities in drought-stricken regions has triggered what the authors call 2026's water wars.
Yeah, the water wars.
When we hear water wars, it sounds like a post-apocalyptic movie. But the sources describe something much more bureaucratic, though honestly equally devastating to the people involved. These conflicts are playing out at local municipal zoning board meetings.
The script details how tech conglomerates are actively outbidding local communities and multi-generational farmers for municipal water rights.
Right.
The disparity in financial capital makes it a fundamentally uneven negotiation. I mean, a tech giant, backed by $1 trillion market cap, can easily afford to pay exponential premium rates to secure millions of gallons of municipal water.
While a local agricultural operation, which is heavily reliant on irrigation, operates on razor-thin margins,
They simply cannot compete.
and the outcome described in the text is grim. Agricultural wells are running dry to support massive, glowing data centers built directly on top of depleting aquifers.
It's a stark contrast.
Now, the tech industry is obviously aware of the optics here. Drying out farming communities is a public relations disaster. So the sources outline the corporate response, which centers around a concept called water offsets.
Right, water offsets. Tech companies are publishing these extensive sustainability reports claiming they are actively replenishing the water they consume, aiming to be, quote, water positive.
Water positive.
The concept is borrowed directly from the carbon footprint playbook. With carbon accounting, a company can emit a ton of CO2 from a factory in one hemisphere and fund the planting of a forest in another hemisphere to offset it.
Because the atmosphere is a global shared commons, the math theoretically balances out.
Theoretically, yes.
Uh-huh.
But the Silicon Drought presentation aggressively attacks the logic of applying carbon accounting to water scarcity.
Yeah, the authors argue that water is intensely, stubbornly local. There's a specific quote from the text that sums up their critique perfectly. You cannot replenish an aquifer with a press release.
That's a great quote. The source makes the case that if a data center drains millions of gallons from an underground aquifer in Arizona, funding a state-of-the-art water purification project in a rural village in India, while an objectively positive philanthropic action.
Right, it's a good thing to do.
It does absolutely nothing to put physical water back into the Arizona aquifer. The local ecosystem surrounding the data center still faces collapse.
And this localized resource grab seems to be part of a much wider strategy. If we look at the metadata from the YouTube channel See Capital Clarity, the video titles suggest that big tech's infrastructure expansion goes far beyond just securing water rights.
The metadata is fascinating. It lists investigative video titles like The AI Energy Trap, Why Big Tech is Buying Nuclear Reactors,
Whoa.
and Sovereignty for Sale, Why Tech Giants Are Buying Small Nations.
Buying nuclear reactors and purchasing land sovereignty, that reads less like a corporate expansion plan and more like the formation of independent tech nation-states.
It really does. The channel's overarching thesis is that to sustain the unprecedented scale of the AI revolution, technology companies are moving away from simply purchasing commodities on the open market.
They want to own the market.
They are attempting to outright own and control the foundational physical resources of human civilization.
That's intense.
The argument is that the cheap, ubiquitous access to artificial intelligence we currently enjoy is being quietly subsidized by the privatization and scarcity of municipal drinking water, land, and energy.
So if the industry is hitting these hard physical limits with evaporative cooling and facing this much localized blowback over water rights, are they engineering any technological workarounds? Like, we can't just keep building cooling towers until the aquifers are literally dust.
Well, the sources do detail the industry's desperate pivot toward new cooling technologies for 2026.
Okay, yeah.
The two major breakthroughs heavily referenced in the briefing guide are closed-loop cooling systems and total immersion technology.
Let's look at total immersion because the mechanics of it sound like straight up science fiction. Instead of spraying water over heat exchangers, what is physically happening inside an immersion facility?
Immersion technology abandons water entirely.
Okay.
Instead, the server racks are lowered directly into massive vats of specialized liquid.
Wait, like dumped into liquid?
Exactly. Because water conducts electricity and would instantly short out the hardware, these vats are filled with highly engineered, non-conductive synthetic oils. Yeah. The servers run completely submerged in this viscous fluid. The oil absorbs the intense heat radiating from the chips. Then, the hot oil is pumped out of the vat, run through a dry radiator system to cool down, and cycled back into the vat.
So because it is a closed loop, the liquid never touches the outside air. There is no massive evaporation plume and theoretically no direct loss of fresh water to the atmosphere.
That's the idea.
So does transitioning to oil solve the crisis? Can we just dunk the entire infrastructure of the internet into giant vats of synthetic oil and save the aquifers?
Well, the sources strongly caution against viewing immersion as a silver bullet.
Why is that?
While it does drastically reduce municipal water consumption, it introduces an entirely new set of logistical and environmental bottlenecks.
Like what?
For one, the infrastructure overhaul required to retrofit existing air-cooled or water-cooled centers into immersion facilities is monumentally expensive and slow.
And I imagine manufacturing millions of gallons of highly specialized synthetic oil isn't exactly a green process either.
Precisely. That is the primary counterargument raised in the briefing guide. The environmental footprint of synthesizing, transporting, constantly filtering, and eventually disposing of millions of gallons of industrial oil presents massive ecological risks of its own.
Yeah, that makes sense.
But more fundamentally, the authors of the Silicon Drought argue that relying solely on engineering to fix this ignores the root cause: unchecked exponential consumption.
Right, because no matter how efficient the cooling loop gets, if the sheer volume of global prompts and multi-billion parameter training runs continues to double every few months, the physical footprint will just continue to expand.
Exactly.
The presentation script proposes that efficiency alone won't stabilize the situation. We need a way to hold the industry accountable and a way for users to actually comprehend the cost of their digital actions. They introduce a new ethical standard for 2026, the WEPT metric.
Yeah, WEPT, it stands for Water Efficiency Per Token. To understand the metric, we have to understand that AI models process language in chunks called tokens, which are roughly equivalent to syllables or parts of words.
Right.
The WEPT metric attempts to calculate the exact fractional amount of water evaporated to generate a single token of output.
It is essentially a nutritional label for artificial intelligence.
I like that analogy.
Because right now, the physical cost of using these tools is entirely invisible to the user. But imagine if every time you open an AI interface to draft an email, summarize a report, or generate an image, there was a mandatory tag next to the Generate button.
A physical cost label.
A label showing exactly how many fluid ounces of your region's municipal reservoir it took to produce that specific output.
The sources advocate for the WEPT metric because it forces immediate consumer-facing visibility onto a completely opaque industrial process. The authors point out a profound overarching irony defining this era of technology, which the tech industry heavily markets artificial intelligence as the ultimate tool for solving complex global crises, with climate change modeling often cited as the primary use case.
Oh, wow. Yeah. They are pitching AI as the software that will calculate the solution to global drought, while the physical hardware running that software is actively depleting local freshwater reserves in real time.
It is a paradox.
It really is.
And that is why the WEPT metric is presented as a crucial intervention. If everyday consumers were forced to look at a WEPT score and physically recognize that their interaction with a digital revolution is being directly billed to the watershed that supplies their community, it alters the behavioral calculus.
It makes you pause.
Right. Is the slight convenience of having an AI instantly summarize an article truly worth the physical depletion of the spring that feeds a local agricultural town?
We've covered a tremendous amount of ground today unpacking these sources. We started with the sheer thermal physics of 2026, the incredible compute density of H200 and X100 chips, generating so much heat that they forced the entire industry to abandon traditional air conditioning for evaporative cooling towers.
And we examined the staggering scale of that water loss. A full liter of pristine fresh water vaporized for every few dozen user prompts, with single facilities consuming the daily water requirement of a 50,000-person city.
We also looked at the toxic reality of the brine problem, where the unevaporated water is returned to the ecosystem as a chemical-heavy slurry.
We tracked how the need for vast space and cheap solar energy pushed these facilities into arid environments like Arizona and Chile.
Sparking those bureaucratic water wars where tech conglomerates outbid multi-generational farmers for a shrinking resource. We heard the source's critique of corporate water offsets, and finally we explored the push for the WEPT metric, an attempt to bring transparency to the invisible physical cost of our digital habits.
The central thesis across all of these materials is that society must undergo a massive shift in understanding. The digital world is not a weightless ether.
Not at all.
It is a heavy industrial machine that extracts a severe physical toll on the planet's most critical resources.
There is one specific visual from the Silicon Drought presentation that really anchors this entire deep dive for me. It's an image of a sleek, highly advanced robotic hand. Resting in the palm of that mechanical hand is an apple.
Right.
But the apple is wilting, turning into liquid, and slowly slipping through the metal fingers. It perfectly visualizes the organic cost of synthetic growth. So, to you, listening to this, the next time you open up a frictionless AI interface on your phone, take 1 second to picture the massive humid cooling towers out in the desert and that silent tap running relentlessly behind the scenes.
As we conclude today's analysis of the source material, I want to leave you with a final question to consider regarding the industry's ultimate engineering hope. If the technology sector successfully achieves a monumental transition away from evaporative water cooling and manages to submerge the entire physical infrastructure of the internet into millions of gallons of synthetic non-conductive oil, are we actually solving the core problem of resource depletion? Or are we simply shifting the insatiable exponential appetite of artificial intelligence away from our aquifers and directly onto a brand new, entirely unforeseen environmental crisis?